In this video, I'm going to talk about the linked list. To understand why the linked list class exists, it's important to understand a few things about the way Java stores information in memory for the array list, and the linked list. Let's start with an array of primitive data types. This is the simplest thing to understand. When an array of primitive types is allocated, space is allocated for all of its elements contiguously, as shown here. You can see from this slide that we have an array of 7 integers. The index position is in the left column, and that's the number we use to access a specific array value. So the first element, when we use index position 0, this will retrieve the value 34. When we use index position 1, this gets the value of 18, and so on. The addresses I show here are memory addresses represented by these numbers. If 100 is the address of an integer, and we know an integer is 4 bytes, then the address of the next integer, if it's contiguous, would be 104, as I show here for the second element. Java can use simple math using the index and the address of the initial element in the array to get the address and retrieve the value of the element. For reference types, meaning anything that's not a primitive type, like a string or any other object, the array elements aren't the values, but the addresses of the referenced object or string. I've talked about this before. There's a level of indirection, as I show on this slide. You've learned that array lists are really implemented with arrays under the covers. This means our objects aren't stored contiguously in memory, but their addresses are in the array behind the array list. And again, the addresses can be easily retrieved with a bit of math if we know the index of the element. This is a cheap or fast lookup and doesn't change no matter what size the array list is. But to remove an element, the referenced addresses have to be re-indexed or shifted to remove an empty space. And when adding an element, the array that backs the array list might be too small and might need to be reallocated. Either of these operations can be an expensive or time-consuming process if the number of elements is large. In this slide, the string, 3.5, represents a new element I want inserted at index position 3. This means all the elements below this point need to be moved and re-indexed. An array list is created with an initial capacity depending on how many elements we create the list with, or if you specify a capacity when creating the list. On this slide I show an array list that has a capacity of 10 because I'm passing 10 in the constructor of this list. I then add 7 elements. I can add 3 more elements using the ArrayList add method, and the array that is used to store the data doesn't need to change. The elements at indices 7, 8 and 9 get populated. But if the number of elements exceeds the current capacity, Java needs to reallocate memory to fit all the elements, and this can be a costly operation, especially if your array list contains a lot of items. So now, if our code simply calls add on this array list, the next operation is going to create a new array with more elements, but needs to copy the existing 10 elements over. Then the new element is added. You can imagine this add operation costs more in both time and memory than the previous add methods did. When Java reallocates new memory for the array list, it automatically sets the capacity to a greater capacity. But the Java language doesn't really specify exactly how it determines the new capacity or promise that it will continue to increase the capacity in the same way in future versions. We can't actually get this capacity size from the array list. From their own documentation, Java states that the details of the growth policy are not specified beyond the fact that adding an element has constant amortized time cost. Okay, maybe you're interested in what constant amortized time is. Let's start with how to determine cost, which in this case is generally considered in terms of time, but may include memory usage and processing costs, etc. Maybe you've heard people talking about Big O notation, or Big O, and wondered what this means. I won't get too deep into it, but there are a couple of concepts that are fairly easy to grasp and will help us understand how cheap or expensive an operation is in terms of time and memory usage as the operation scales. This means it's a way to express how well the operation performs when applied to more and more elements. Big O approximates the cost of an operation for a certain number of elements called n. Cost is usually determined by the time it takes, but it can include memory usage and complexity, for example. As n, the number of elements, gets bigger, an operation's cost can stay the same. But cost often grows as the number of elements grow. costs can grow linearly, meaning the cost stays in step with the magnitude of the number of elements. Or costs can grow exponentially or by some other nonlinear fashion. In a perfect world, an operation's time and complexity would never change. This ideal world in big O notation is O1, sometimes called constant time. In many situations, an operation's cost is in direct correlation to the number of elements, n. In big O notation, this is On, sometimes called linear time. So if we have 10 elements, the cost is 10 times what it would be for one element, because the operation may have to execute some functions up to 10 times versus just once, and 100 times for 100 elements, for example. On is generally our worst case scenario for list operations, but there are big O notations for worse performers. We won't be talking about exponential growth or nonlinear growth yet, since it's not relevant to our discussion here. Another scenario is the one the Java docs declared for the growth of the array list, that adding an element has constant amortized time cost. In our case, we'll designate this constant amortized time as O1 star. This means that in the majority of cases the cost is close to O1, but at certain intervals the cost is On. If we add an element to an array list where the capacity of the list is already allocated and space is available, the cost is the same each time, regardless of how many elements we add. But as soon as we reach the capacity and all the elements, all n elements, need to be copied in memory, this single add would have a maximum cost of On. After this operation that forced a reallocation, any additional add operations go back to O1 until the capacity is reached again. As the expensive intervals decrease, the cost gets closer to O1, so we give it the notation O1 star. This slide shows the big O values for the most common array list operations or methods. Let's just talk about one example, the contains method, which looks for a matching element and needs to traverse through the array list to find a match. It could find a match at the very first index. This is the best case scenario, so it's O1. It might not find a match until the last index. This is the worst case scenario, so it's On. In general, the cost will be something in between for the contains method because the element will be found somewhere between the first and nth or last element. You'll notice that the indexed methods are usually O1, remembering that finding an element by its index is a simple calculation. It only gets costly with indexed add or remove methods if the array list needs to be re-indexed or resized. Now that you understand why some operations are more efficient and less costly because of indexing, it's time to look at linked list. The linked list is not indexed at all. There is no array storing the addresses in a neat ordered way, as we saw with the array list. Instead, each element that's added to a linked list forms a chain, and the chain has links to the previous element and the next element. This architecture is called a doubly linked list, meaning an element is linked to the next element, but it's also linked to a previous element in this chain of elements. The beginning of the chain is called the head of the list, and the end is called the tail. This can also be considered a queue, in this case a double-ended queue, because we can traverse both backwards and forwards through these elements. Getting an element from the list or setting a value of element isn't just simple math anymore with the linked list type. To find an element, you'd need to start at the head or tail and check if the element matches or keep track of the number of elements traversed if we are matching by an index because the index isn't stored as part of the list. For example, even if you know you want to find the fifth element, you'd still have to traverse the chain this way to get that fifth element. This type of retrieval is considered expensive in computer currency, which is processing time and memory usage. On the other hand, inserting and removing an element is much simpler for this type of collection. In contrast to an array list, inserting or removing an item in a linked list is just a matter of breaking two links in the chain and re-establishing two different links. No new array needs to be created, and elements don't need to be shifted into different positions. A reallocation of memory to accommodate all existing elements is never required. For a linked list, inserting and removing elements is generally considered cheap in computer currency compared to doing these functions in an array list. All of that being said, there is a lot of debate about whether a linked list is ever really a preferred solution over the array list, especially as the Java language improves in performance and computer hardware itself continues to improve. I won't wade into this debate, but I want to encourage you to review both sides of the debate if you're interested. Let's look at the big O notation for the matching operations in a linked list. This slide shows the big O values for the most common shared list operations or methods for both types. For a linked list, adding elements to the start or end of the list will almost always be more efficient than an array list. When removing elements, a linked list will be more efficient because it doesn't require reindexing, but the element still needs to be found using the traversal mechanism, which is why it is ON as the worst case. Removing elements from the start or end of the list will be more efficient for a linked list. So let's review what all of this means. The array list is usually the better default choice for a list, especially if the list is used predominantly for storing and reading data. If you know the maximum number of possible items, then it's probably better to use an array list, but set its capacity. This code demonstrates how to set the capacity of your array list to 500,000. An array list's index is an int type, so an array list's capacity is limited to the maximum number of elements an int can hold. Integer.max value equals 2,147,483,647. You may want to consider using a linked list if you're adding and processing or manipulating a large amount of elements, and the maximum elements isn't known but may be great, or if your number of elements may exceed integer.max value. A linked list can be more efficient when items are being processed predominantly from either the head or tail of the list. I'll explain methods for this in more detail coming up. In the next video, I'll just show you a few significant differences between the linked list and the array list, in addition to these behind-the-scenes differences I've discussed here.